Scientists ask questions. And I'm here today to share some of those questions with you. Why are we here? Why are we sitting on a planet that's orbiting the sun? Why is the sun one of 100 billion stars in our Milky Way? And why is our Milky Way one of 100 billion or so galaxies in the universe? In short, why is the universe looking as it does? And how might the most violent event in the universe and the most feeble signals help us answering those questions? Now, about a year back, on the 14th of September 2015, we saw something that might help us answering those questions. To understand that, I have to take you back by about 100 years to Zurich, Switzerland, in 1915, when Albert Einstein put the finishing touches on the general theory of relativity. One of the predictions of that theory are gravitational waves. Now, what are gravitational waves? Well, you all know static gravity, which is effectively what keeps your backsides on those seats here. And you might know static electricity, which is what keeps styrofoam attached to kittens. Now, you also might know that electromagnetism can come as a wave as well. You have heard about electromagnetic waves, or as we usually call it, light. And gravity works as well like that. Gravitational waves are propagating through the universe. Now, gravitational waves are causing changes in distances by a very, very small amount, though. So Albert Einstein himself thought, well, that's pretty cool stuff, but we are probably never able to detect those because the changes are too small. Now, genius that he was wrong. But if you think back what we knew about the universe 100 years ago and what we know today about the universe, maybe he can be excused for being wrong. 100 years ago, we didn't know about black holes. Despite the fact that they are a consequence of Albert Einstein's theory, they were only taken seriously as real, something that really exists in the universe about 80 years ago. Today, we even make movies about black holes, but in those times, we didn't know. Also, we didn't know how stars work. Everybody knew about stars, but it was only 80 years ago that we understood that stars are really fusion reactors, that they live and they die, and once they die, they can go with an almighty bang, which is called a supernova. This that you see there is the debris of the supernova, which exploded about 1,000 years ago in 1054 and was observed by Chinese scientists, the first record we have of a supernova. This is nowadays known as the Crab Nebula. And in the middle of that nebula, if you could see it, you would see a tiny black dot, a neutron star, which is left over when a supernova blows off. And this neutron star has about the size of our sun, the mass of our sun, rather. The size is about 10 kilometers, so about the size of The Hague. It's an incredibly dense object. And it turns out if you whisk those things around, or if you look at what happens during a supernova, you realize those things can emit gravitational waves. And they can emit gravitational waves that we might be able to detect. So about 50 years ago or so, people started to take that seriously and said, well, let's build a detector for gravitational waves. This is the first one. There's a guy called Joe Weber bent over it. He invented it. It's just a metal cylinder, and when a gravitational wave passes by, it should ring that like a bell. Now the theory is sound, it rings like a bell. Unfortunately, all the gravitational waves we know of are way too weak to be detected with this thing. So about 40 years ago, people started thinking about a different measurement principle. Let's use light to measure gravitational waves. And then 25 years ago, people started building a real big detector. This is the LIGO site in Hanford, state of Washington, in the middle of the desert. You see the building there in the lower right. It's a rather big building. If you look closely, you might see trucks. You probably don't see people because they are too small. And it's a huge detector. The little building that vanishes at the horizon is about 4 kilometers away. So we are talking 2 times 4 kilometers of vacuum tubes, about a lot of laser light, a lot of instruments in there, and you encounter challenges, and you overcome the challenge. And behind this challenge lies the next challenge. You overcome that as well. Sometimes you encounter things that are not really a challenge, but just amusing. So my favorite story there is, you know, if you send a laser light like to there, I hope I don't hit the camera, it goes straight, right? If you do that for 4 kilometers, and you do that on the surface of the Earth, you have the problem that the Earth isn't straight. So you have to carve away the Earth. So when they built that, when they laid the foundation for that detector, they had to make it flatter than flat. Now, 25 years, it's a lot of time, and for sure a lot of money. But what I'm going to show you would not be possible without the dedication of thousands of people that were curious enough to help out with the construction and the building of this detector. So a year ago, 14th of September 2015, this detector found that. That is the signal of a gravitational wave. Now, Einstein was wrong, right? We could detect them. We detected that. And I told you, gravitational waves change the distances. Now, by how much changed the distance by this gravitational wave? Well, consider the distance between the Earth and the Sun. This wave changes it by about the diameter of an atom. It's kind of not a lot, but we can measure it. I told you Einstein was wrong, but Einstein was beautifully right as well. You see this little yellow word predicted up there, and you see the nice yellow line following precisely the thick orange line. This is the prediction from general relativity. So Einstein was right as well, because his theory allows us to calculate such a signal. Now, the curious thing about that signal really is that if you were involved in the building of the detector, obviously you run a book, what is the first signal we detect? And pretty much everybody said, well, it will be probably something in our galaxy, or maybe just a galaxy around the corner. It turns out that this signal is something we didn't expect. It comes from 1 billion light years away, and it is certainly far outside our galaxy. It's an extragalactic signal, and it's caused by massive black holes, 2 black holes that are crashing into each other, each of them weighing about 30 times the mass of the Sun. So you switch it on, the first thing you see is something you didn't expect. This is why people call that a new window to the universe. You all of a sudden see things you have never seen before. But this is just the beginning. Imagine the future. In about 15 to 20 years or so, we will have detectors like that in orbit, not 4 kilometer size, but millions of kilometers in size. And we won't be bothered with objects like 30 solar mass black holes. We are going after the monsters that lurk in the center of galaxies. Each of the galaxies that we know, we think has a black hole in the center that weighs millions the times of the black hole of a sun. So when those 2 galaxies collide, like these 2, where you see the bright spots in the center, this is where probably black holes are. If those 2 galaxies collide, the 2 black holes collide and will give you a signal. And remember one of the big questions: why does the universe look as it looks like? Well, if we see those galaxies merging, we can see how galaxies have been assembled over time, from effectively the time when matter first formed in the universe. Consider that when we switched the detector on, the LIGO detector, it took us only a week to detect something. And it was something we've never seen before. Now, imagine we switch on a bigger detector. We now think that we see those galaxies merging. But think about the things, imagine about the things we don't know yet. And this detector and the gravitational waves have the big potential to completely change the view of the universe that we have today. And again, this is just the beginning. Thank you very much.